So today we're going to talk about section 15.2. 15.2 describes double integrals over more general regions. Up until today we've only talked about Riemann integration when we had rectangular regions as our region of integration, as the base of the volume of our solid. But let's say that we want some other shape. Now we'll know how to do it. So in order to get us to the point where we can do that type of integration, I'm going to spend some time setting up what it is to be a type 1, a type 2, or a type 3 region. So we're going to talk about 3 different types of regions that will be our building blocks rather than rectangles for the bases of our region. Next, I'm going to describe piecewise regions which are made out of type 1 or type 2 or type 3 regions. We're going to work on computing double integrals over type 1, type 2, type 3, and piecewise regions. So that's actually using the fact that we can describe these regions, and then we're going to find the volumes on these regions. And then finally, we're going to have to figure out sometimes, given a word problem or a practical valued problem, we're going to have to figure out what is the region of integration and compute double integrals after finding those regions of integration. So to start off, I want to give some examples of types of regions. We're taking a step away for a second from our integration, and we'll incorporate integration back in a second or two, but I think that it's helpful to think about regions all on their own for a little bit. So when I'm talking about regions, I'm talking about parts of the xy plane. So I'm thinking of just the xy plane, and I want to know, let's say that I have a region that looks something like this. Let's say I have a half circle, and this half circle is of radius 2. And I want to be able to describe algebraically what is going on in this region. What are the bounds on this region, essentially, is what I'm asking. And in order to do that, I have to describe algebraically how would I describe this. So recall that we know that x squared plus y squared plus the radius squared would describe the full circle. But I don't want the full circle, right? I only want this part of the circle. So how would I be able to describe this so that I only have the top half of the circle? The easiest way to do this, I think, is to solve this as a function of y. So I get that the whole circle itself would be given by y is equal to, I'm going to subtract, maybe I'll write it out clearly. Y squared is equal to 4 minus x squared. And then to solve for y, I'm going to take the square root of both sides. And by square rooting both sides, I get that y is equal to plus or minus the square root of 4 minus x squared. This is exactly the whole circle. So I'm finding the outer boundary of this region. But notice that I don't want the bottom part of the circle. I only want the top part of the circle. So what I'm thinking to myself is that my y values in this case are going to go from y equals 0 down along this flat line up to the top of the circle. And the top of the circle is given by positive square root 4 plus x minus x squared. So in conclusion, I'm saying that my y values in this case are going to range from y being less than or equal to 0 all the way up until y is less than or equal to the square root of 4 minus x squared. Because this top part of the circle has the equation y equals the square root of 4 minus x squared. So these are the bounds on my y values. My y values shouldn't get less than 0 because I don't want the bottom half of the circle. And my y values shouldn't get greater than this square root of 4 minus x squared, because that would put it up and above where this circular region is. But this is only describing my y values. I also want to know what are the bounds on my x values. And in this case, because I've already bounded the heights of each of these, I only need to know how far in each direction the x's will go. Because if I only wanted the quarter circle, my x values would just go from 0 to 2. But because I want the whole top of the half circle, it means that my x values in this case are going from -2 to 2. So what we've just described here are the bounds on this region. And this is the way that I would describe the bounds on the region. This particular example I'm going to call a type 1 region, and we'll see some more examples as well. Type 1 regions, in general, are given where the bounds on my y values are functions of x. So sometimes we call it phi of x is less than or equal to y is less than or equal to gamma of x. Whereas my x values are just going to go from constant to constant. This is a type 1 region because the bounds on my y are functions. It turns out that in this case, the lower bound is also just a constant. But the upper bound is certainly a function of x, whereas the bounds on x are just flat numbers. They go from -2 to 2. So this is my definition of a type 1 region. Let's see another example of a type 1 region. So for my next example of a type 1 region, let's consider we're still in the xy plane. We're going to stay in the xy plane when we consider all of our regions. And let's say that I have the curve given by y equals x squared, that's this parabola drawn in blue. And let's say that I also have the straight line y equals x, which is drawn here in green. And let's say that my region is going to be the area between these two curves. And I want to be able to describe this region as a type 1 region. So again, let's recall what that means. I need to think about what are the bounds in my, I'm thinking of slicing this up, and I want to know what is the lower bound on my y values and what is the upper bound on my y values. In this case, the lower bound is going to be the curvy parabola, which means that my y in this case, y is always going to be greater than or equal to x squared. This is my x squared curve. I know that y is greater than it because y is going up above my x squared curve. It's going above my x squared curve, but it's not taking up the whole area above the x squared curve. It's also bounded by my y equals x curve. So in this case, maybe I should have done this more color-coded. Check this out. My bounds on my y, the lower bound on the y is the lower part, which is the curvy x squared curve. And the upper bound is going to be the curve where y is exactly equal to x. So this is a type 1 region because I have a function of x, which is less than y, and a function of x, which is greater than y, and those are the bounds on my y function. But we aren't quite done. To describe this region fully, all of the region that contains this, I need to make sure that I cut it in the right places. That if I only wanted half of it, my x values might stop here and go to here, but I want the entire region here. And it turns out that that means that my x values in this case are going to go from this intersection point to this intersection point. And this intersection point is exactly where x is equal to 0, and this intersection point is exactly where x equals 1. And that's because where the intersection point is where y equals x squared is equal to x. And I can see that that solution is given by, well, I actually could do a bunch of algebra and say that that means that it's where x squared minus x equals 0. I'm setting these equations equal to one another. And that happens when 0, oops, I factor this. These intersections take place when x is equal to 0 or when x minus 1 is equal to 0, which is at a value of 1. So I just found out then that my bounds on my x value are going to be 0 is less than or equal to x is less than or equal to 1. This is another example of a type 1 region. So I've done a couple of examples of type 1 regions. Let's take a look at what it means to be a type 2 region. And I'm going to use the same example as we used before, only I'm going to set it up differently. So instead of thinking of these vertical slices and thinking what are the bounds on my y values, I'm going to think of setting up my region so that it's sliced horizontally. And I want to know what are the bounds on my x's and what are the bounds on my y's. In this case, my x values are going to be smallest when they're down here touching where y equals x, and they're going to be biggest when they're out here touching this curve where y equals x squared. So the bounds are very similar, but the difference is instead of writing it in terms of a function or where y is equal to a function of x, I'm going to write it as x being equal to a function of y. So in this case, I can rewrite this function, the green function, rewritten as a function of y, is actually just the same function, that x is now a function of y, where x is just equal to y. However, if I want to write this function as a function of y, I'm going to have to take the inverse of the function. And I find that if I square root both sides of this, I get that x is equal to the square root of y. So what did I do? I took the square root of both sides to solve for x, and that told me that if I wanted to write x as a function of y, I would be given this curve. So my bounds on x in this case, the lower bounds are going to be the ones that are closer to where x equals 0. So x equals 0 right along the y-axis. So the lower bounds are going to be where x is equal to y. And that's always going to be less than or equal to my x values, because my x values are always going to range somewhere between where x is equal to y on the green line, and then they'll go up as high as x equals square root y on the blue line. So these are the bounds on my x values, and the bounds on the y values actually are going to be just where this y value is equal to 0 all the way up until this y value, which is equal to 1. So I just rewrote this, instead of as a type 1 region, I've now rewritten it as a type 2 region, and I'll write the definition over here. So a type 2 region is one where my x values are bounded by functions of y. So I have some function of y that's the lower bound on my x's, and some function of y that's the upper bound on my x's. And my y values are trapped between constants. And my final definition is that a type 3 region is a region that is both type 1 and type 2. So this is an example actually of a type 3 region, because it's one that is both a type 1 region. We saw an equation for it as a type 1 region, and we also have it as a type 2 region, because this was an example of it as a type 2 region. So type 3 is both type 1 and type 2. And the reason why it was both type 1 and type 2 in this case is the fact that these curves are meeting at points. So it was easy to have fixed values for those, although there are other cases as well.